Hi, good morning everyone. I am K. Murthy. I work as an assistant professor in the Government First Aid Women's College, Tumkur. This is my 24th video for the second semester BSc students of Tumkur University, and the subject which I am presenting is the physics. In that, this is my 24th video. I can say in the second unit it is the 9th video. Second unit is all about the magnetostatics. There we come across two important laws in the magnetostatics. One is the Biot-Savart's law, another one is the Ampere circuit law, and we applied this for many cases and solved the many problems with these two important laws of magnetostatics. After that, we discussed about a very sensitive instrument which is called ballistic galvanometer, which is used for the measurement of a small discharge for a short interval of time. Small charge which is flowing for a short interval of time can be measured with the help of a very sensitive instrument called ballistic galvanometer. We studied how it has been constructed and what is the theory behind it and what will be the equation for the charge which is flowing through the ballistic galvanometer and how we can calculate the charge which is flow through the coil of the ballistic galvanometer. Now today in this 24th video I am going to discuss about the application of BG. Before going to the application of BG, we need to know some of the important definitions regarding this ballistic galvanometer. The first thing which I need to tell in this thing is the charge sensitivity. So charge sensitivity of a ballistic galvanometer is defined as the deflection produced in the coil per unit charge. I mean to say, if you send unit charge to the coil, we have a coil in the ballistic galvanometer which is placed between the two strong permanent two poles north and south. When you give an unit charge to the coil, see how much deflection it has produced, and that is called charge sensitivity. The deflection in the coil which is produced for unit charge is known as charge sensitivity, which we are representing it by the symbol SQ, which is equal to theta by Q. We know what is Q is. Q, it is C divided by N by NAB T by 2 pi into theta, which I derived in my last video. If I rearrange that little bit, so if I do theta by Q, and it will be NAB by C into 2 pi by T. This is the equation of charge sensitivity, and this equation will be more helpful in solving the numerical problems which is related to the ballistic galvanometer. After that, you need to know one more important definition, that is current sensitivity. The name itself indicates, with the name itself you can define this quantity. This current sensitivity of a ballistic galvanometer is defined as the deflection produced in the coil per unit current. I mean to say, if you pass an 1 ampere current to the coil, this coil is getting deflected. So that deflection is known as current sensitivity. The deflection which is produced when you pass a current of 1 ampere to the coil of the ballistic galvanometer. Right, the symbol is SI. It is theta by I, deflection per unit current. So if I rearrange the equation which I got when deriving an equation for the charge in the ballistic galvanometer in my previous video, so it will be NAB by C. Theta is equal to NAB by C. Now one more definition is the voltage sensitivity of the ballistic galvanometer is defined as the deflection produced in the coil per unit voltage. If you establish a unit voltage and see the deflection which is produced in the coil, and that deflection is called as the voltage sensitivity. That means to say it is the deflection produced in the coil when there is an unit voltage. Right. It is again represented by SV, which is theta by V. We know what is V is. From the Ohm's law, V is equal to I into R. So it is theta divided by IR. If I split this, in one bracket I'll write theta by I, and the other bracket I'll write 1 by R. Why I am writing this? Because I'll get some quantity in the first bracket which is theta by I, and that quantity is called the current sensitivity of the galvanometer. This theta by I, the quantity in the first bracket, is the current sensitivity, and I know the equation for current sensitivity. It is NAB by C. So for theta by I am writing NAB by C, and 1 by R is attached to that. It is NAB by CR will gives us the equation for the voltage sensitivity of the ballistic galvanometer. Right. There is one quantity which we can define here is the figure of merit. Figure of merit of a BG is defined as the current required to produce deflection of one division on the scale which is at 1 meter from the mirror. I told you the lamp and scale arrangement. Light is incidenting on the mirror which is attached to the phosphor bronze wire. That means the suspension wire of the coil. Okay. So if light is fall on the mirror and it is getting reflected on the scale, this system is known as lamp and scale arrangement. Light is incident on the mirror from the lamp and it is reflected on the scale. We will see the movement of light spot on the scale. From that we can write the deflection. Okay. So now what is the thing is, the current which is required to produce a deflection of one division on the scale. If the light spot moves one division from that current, then that current is the figure of merit. It is given by reciprocal of current sensitivity also. So figure of merit is 1 by SI, which is I by theta. This time figure of merit is not the deflection, it is the current which is required to produce one division deflection on the scale. So it is reciprocal of the SI, which is the current sensitivity, which is I by theta, and that is equal to C by NAB. Students, you need to know all these equations. One is the charge sensitivity, current sensitivity, voltage sensitivity, figure of merit, which is reciprocal of the current sensitivity. It's all because of while solving the problems, numerical problems related to these magnetostatics, you need all these equations. So you write down an equation in a separate page, memorize this, because this will be helpful in solving numerical problems which is related to the BG. Right. Deadbeat galvanometer. So a galvanometer which comes to rest quickly without vibration or oscillation is known as deadbeat galvanometer. If the oscillations of the coil, if it comes to rest very quickly, then such a galvanometer is known as deadbeat galvanometer. So what is the condition for deadbeat galvanometer? What is the condition for coil which comes to rest very quickly without a vibration or oscillation? So what could be the reason for that? What is the condition which support this deadbeat galvanometer? Which supports this quick rest of this coil. Okay. The first condition here is the period of oscillation must be small. The period of oscillation of coil must be small. It has to oscillate with a very small period. Number of oscillations per second must be very small. Then only the coil will comes to rest very quickly. So for that, to make the period of oscillation small, you need to have the moment of inertia of the coil must be very small. T is equal to 2 pi root of I by C is the formula. Formula for period of oscillation is, which I told you in the derivation in my last previous video, which is T equals 2 pi root of I by C, where I is the moment of inertia. You can say that T is directly proportional to the moment of inertia of the coil. So if T has to be small, means the moment of inertia has to be small. So make the moment of inertia small. You know how to make the moment of inertia, and what is moment of inertia? It is a mass into square of the distance from axis of rotation. Either you reduce a mass or you reduce the distance of this mass distribution from the axis of rotation, the moment of inertia will get reduced automatically. If that get reduced, then period of oscillation will get reduced. If period of oscillation is get reduced, the coil will comes to rest very quickly. Right. Second reason is damping must be very large. So what is damping? You need to bring the oscillations quickly to the rest. That is called damping. For this, coil must be mounted on a conducting frame. Okay. So this coil which is wound on a frame has to be conducting, because that produces eddy current. That eddy current will stop the oscillation of the coil. So you need to wound the coil on the conducting frame. That makes the oscillations comes to rest very quickly, and that is known as damping. These are the two things. One is period of oscillation must be small by decreasing the moment of inertia of the coil, and second, damping is done by wounding the coil on a conducting frame. Condition for ballistic galvanometer or a periodic galvanometer. If you want to increase the period of oscillation of a coil, what must be done first is you need to increase the moment of inertia. So increase the moment of inertia. Suspension wire must be comparatively thinner this time. Suspension wire must be comparatively thinner so that you can increase the moment of inertia. And one more thing is damping has to be very small. That can be done by wounding a coil on a non-conducting frame, non-metallic frame. If you wound a coil on a non-metallic frame, it takes longer time to oscillate, because of there will be no eddy current, there will be no opposition for these oscillations. So damping will be certainly small if you use a non-conducting frame for the coil. Right. So this is the actual topic I wanted to discuss in the video. This is one of the application of ballistic galvanometer. The first application of ballistic galvanometer is the high resistance can be calculated by a method called leakage. You know what is BG, which BG measures the sudden flow of charge for a short interval of time. It only measures the charge which is flowing suddenly for a short interval of time. Okay, right. So what's actually the principle behind this method of finding the high resistance by leakage is, first the capacitor is fully charged, then it is discharged through high resistance for a known time t, and then remaining charge is discharged through a BG, and see the corresponding deflection in the BG, and you can calculate the high resistance R. Okay, did you got this? So first charge the capacitor, then discharge it for a high resistance for a known time, then the remaining charge on the capacitor is allowed to discharge through BG, and BG shows the deflection. Note down the corresponding deflection. From that deflection you can measure the high resistance R. Okay, right, this is the setup which you need to make to find the value of this high resistance R. Okay, right, we'll see what has to be done. First, the capacitor is charged to a maximum value of Q0 by pressing the key K1. Yeah, see the diagram. If you press the capacitor, then that circuit will be closed. When you press the key K1, you will have only the battery and the capacitor. Okay, if you press K1, you will have only the battery and capacitor in the circuit. So therefore the capacitor gets charged to a maximum value of Q0. Now the capacitor is charged. So what has to be done next? Now the charge fully charged, then it is allowed to discharge through BG by pressing the key K3. Now press the key K3. The charge on the capacitor will discharge through BG. Okay, now let's note down the theta naught, throw in the BG. Theta naught is the throw in the BG when capacitor is fully charged and then discharge through BG. Okay, so note down the value of theta naught. We know that the charge on the capacitor Q is equal to C into V. Q naught, you can say it is C into V naught. So we have an equation for the charge Q is equal to K dash theta naught into 1 plus lambda by 2. But this is absolutely a new equation I am writing this time. Because when you look for the effect of damping, where you have number of throws of the BG, one is theta 1, theta 2, theta 3, theta 4. Left side you will have theta 1, theta 3, theta 5 and theta 7. And right side you will have theta 2, theta 4, theta 6. This kind of reflection. If I take ratio theta 1 by theta 2 and theta 2 by theta 3, theta 4 by theta 5, and that is equal to the decrement D. I am calling the ratio of successive deflection which is produced in the BG as the decrement D. If I take a logarithm of D, log D will be called as logarithmic decrement. Log D is lambda. You know what is D is. D is the ratio of successive deflections, theta 1 by theta 2, which is equal to theta 3 by theta 4, which is equal to theta 2 by theta 3, theta 3 by theta 4, which is equal to theta 4 by theta 5, and that is called D. D is the decrement. Okay, right. After knowing the decrement, we are defining a new quantity which is called logarithmic decrement lambda, which is log D, and D equals e to the power of lambda. So I can write theta 1 by theta 2, theta 2 by theta 3, theta 3 by theta 4 as e to the power of lambda. Okay, for one complete deflection, this is theta 1, first throw, then it goes to theta 2, then again comes it is theta 3. So going from here and coming back, theta 1 and theta 3 will make one complete oscillation. If I take theta 1 by theta 3, it will be theta 1 by theta 2 into theta 2 by theta 3, which is equal to e to the power of lambda into e to the power of lambda, which is equal to e to the power of 2 lambda. Okay, if I take 1/4 of oscillation, it will be e to the power of lambda by 2. So then theta by theta 1, where theta is the first correct deflection and theta 1 is the first observed deflection, if I take the ratio of theta by theta 1, so it will be equal to 1/4 of oscillation, which is e to the power of lambda by 2. If I cross multiply, theta equals theta 1 into e to the power of lambda by 2. So if I expand the series of e to the power of lambda by 2, it is 1 plus lambda by 2. Then theta is equal to theta 1 into 1 plus lambda by 2. So where in the equation of the BG, means while deriving the theory of BG, I got the equation for Q as K dash theta. It is K dash theta. Theta is the first correct deflection and where theta naught is the observed deflection. So from correct deflections to observed deflection, you need to add this term 1 plus lambda by 2. Students, now you got the how I derived this equation. So theta is the first correct deflection, theta naught is the first observed deflection. So you are only seeing the observed deflection, not the correct deflection. Convert it, so you have to write theta naught into 1 plus lambda by 2, where lambda is the logarithmic decrement. Right, this makes the equation 1. Now again the capacitor is charged to a same value. Be careful, you need to charge the capacitor by to a same value by pressing the key K1 for the same period of time as you did before. While charging the capacitor first time, how long you pressed key K1, you need to note down that, and you have to again press the key K1 for the same period of time to charge the capacitor to the same value. This charge is allowed to leak through the high resistance for a known interval of time. You note down the time and discharge the capacitor, and it allow the capacitor to leak through the high resistance for a known time. Say some 1 minute or 2 minutes, you allow the charge on the capacitor to leak through the high resistance and note down that time by pressing the key K2. Then the remaining charge on the capacitor is allowed to discharge through BG by pressing the key K3, and the throw on the BG theta 1 is noted. So first I got theta naught. I noted the theta naught. First I charged the capacitor and discharged through BG, and I noted the value theta naught. This time what I am doing, I am charging the capacitor to a same known value and then leaking the charge on the capacitor for a known interval of time t through the high resistance R, and again the remaining charge on the capacitor is allowed to discharge through BG, which gives the throw of theta 1. You have to know one thing, if charge goes through the BG, it gives a throw. So it gives a theta, it gives an angle theta. The spot will move on the scale, and you have to note down the theta. That's what the BG is. That's how BG works. If charge goes through the ballistic galvanometer, it gives the deflection. The coil of the BG is get deflected. You can note down the deflection by the looking at the spot which is moving on the scale. First you need to note down the spot which is moving on the scale by charging capacitor and discharging through BG, which is theta naught. Second time, charge capacitor, allow the charge to leak through high resistance for a known time t, and the remaining charge is discharged through BG, and note down the throw which is theta 1. Right, just a minute. Yeah. Now you have to note down the charge this time, which is, you have to calculate the charge Q1 as CB1, which is K dash theta 1 into 1 plus lambda by 2. Okay, where V1 is the potential across the capacitor after leakage. Right, if I divide equation 1 and equation 2, I will get Q0 by Q1 as V0 by V1, that's equal to theta 1 by theta 2. Sorry, theta naught by theta 1, where theta naught is the first deflection which I have noted, and theta 1 is the deflection which I have noted second time. Now the discharge of the capacitor is a well-known equation. The charge remaining on the capacitor Q1 equals Q0 e to the power of minus T by RC. This is a well-known equation which we have seen in the second PUC. Right, if I rearrange this, I will get Q0 by Q1 equals e to the power of T by CR, where Q1 is the charge remaining on the capacitor after leaking through the high resistance for a time t. Now taking log on both sides, if it's log of Q0 by Q1 equals, this time it was e to the power of T by CR, now it has become T by RC. I need R here, so R is equal to T by C log of Q0 by Q1. Okay. Now from equation 3, what I get is Q0 by Q1 as theta 1 by theta 1. You substitute that here. So our equation of R becomes T by C log of theta naught by theta 1. So this is a natural logarithm, but you need to convert this to base 10 by multiplying this with 2.303. So then R equals T by 2.303 log of theta naught by theta 1, where T is the time, known time for which the charge on the capacitor leaks through the high resistance. C is the capacitance of capacitor. Deflection is the theta naught, which I measured in the first case. Theta 1 is the deflection I measured in the second case, and R is the value of high resistance, which can be calculated by noting all these factors. By knowing all these terms, by knowing all these quantities, I can easily calculate the value of high resistance by the method called leakage. And also I can plot a graph of log theta naught by theta 1 versus T, which I got a straight line. From that I can find the slope. From the slope also I can get a formula for that. R equals 1 by 2.303 C into slope. Slope is simply log theta naught by theta 1 divided by T will gives us the slope. So draw the, plot the graph, get the slope and substitute here and find the value of high resistance by the method of leakage. So this is one of the application of BG where we are finding the value of high resistance using ballistic galvanometer. Just by knowing theta naught and theta 1 means the deflection of Bg in the first case and deflection of Bg in the second case, and by measuring the time for which the charge will leak through the high resistance and the value of knowing the value of capacitance, you can easily calculate the value of high resistance by method called leakage. Okay, so thank you very much.